Thank you very much indeed for everyone. We're going to change the topic slightly from AI to something that's probably as important, if not more so, which is our attempts to fight climate change and get to net zero, this phrase that's used often by governments around the world to talk about how they can increase their energy use, perhaps, all without affecting the environment in total. And that's a problem not only for governments, it's a problem for industry, it's a problem for all of us, and there are many, many technological challenges and routes to it. So I'm very pleased to have Gavin Towler and Arvind Bodhankar to help us understand the challenges and the problems. Gavin, I'm going to start with you, if you don't mind. Tell us a bit about your role at Honeywell, but also how can we get to net zero without running into things like the problems that happened in Spain and Portugal recently, where the electrical grid just fell over. The electrical grid is incredibly important. We don't want it to fall over, but we also need to change the technology radically. Just you go.
Hi, Locke. Well, thank you very much for inviting me to be on the panel. My name's Gavin Towler. I'm the Chief Scientist for Sustainability at Honeywell, so I lead all of Honeywell's activities around safety, environmental impact, and social impact of our technologies. So to the question, as one of the key steps in getting to net zero, obviously, is to get to net zero electricity, because many of the other industries and things that need decarbonizing, the answer is to electrify. And so you have to have a clean electric grid. And that means pushing up the level of wind and solar power. And as we saw with the outage that happened in Spain and Portugal a couple of weeks ago now, at high levels of renewable power, the grid can become unstable. Actually, that's nothing new. The same thing happened in Australia in 2010. And South Australia made a lot of changes to their grid after that. They now run at much higher levels of renewable without being unstable. But we're seeing cases around the world. Barbados had a case a couple of years ago again where they crashed their grid. So very high levels of renewable power, because renewable power is intermittent, can make it difficult to maintain the grid stability. And what happens is if you have fluctuations, so you have a day when a lot of clouds are blowing past, you can have variability up and down of the supply of renewable energy, and that can crash the grid. There are simple solutions in the near term. So between 50, 80% renewables, you actually don't need to put in a lot of energy storage. You need more grid-forming inverters, you need not more firm generation power, but things like synchronous condensers that allow you to control the grid better. And that's what's been done in South Australia. That's also what we've been doing, actually working with the Barbados Light and Power in Barbados. Spain was actually very low in those technologies. The UK also operates at much higher levels of renewable power, and they have the technologies that form a stable grid. At higher levels, you have to, though, go to having some energy storage, either batteries or pumped hydro. And we're seeing a lot more activity now in terms of battery energy storage systems. And there's a nice trick with battery energy storage, because when you put in batteries, you can also build more microgrids. And microgrids give you more stability. They give you the ability to shed loads much faster and then rebuild the grid faster, instead of having to go from what's called a black start, where you lose the power and then it takes a long time to restart things.
So I think the key there is to say that renewable energy is not necessarily going to be a reason to worry about intermittency and all the other things. You can manage it.
Yeah, that's right. This is something that technically the solutions are out there, and it's really just a case of making sure that the grid operators are implementing them.
Arvind, can I come to you?
Sure.
You work in an industry that is notoriously difficult to decarbonize, and it's your job to decarbonize it. So I'm curious how you merge those two things. Steel and cement, these are things that take up a lot of energy, emit a lot of carbon, but they're also fundamental to the world. What are the sort of steps you start to take to decarbonize those?
So thank you, Alok, and thank you, GITEX, for inviting me to speak over here. It's always a pleasure to speak at the GITEX event. I had been a part of Singapore event as well. Coming to the question which you asked about is, cement and steel are really hard to abate sector, and especially the developing economies like India, where 2/3 of development is still yet to come. There it's really challenging. We need lot of limestone, we need lot of coal, we need lot of iron ore. So a lot of mining activities would happen to produce this. And as you know, that steel contributes to almost 12% to the CO2 pool, and cement contributes almost 7 to 8% to to the CO2 pool. So obviously both these things are essential things for the development, and since India and the emerging economies are developing right now, we need steel and cement. Without that we can't work about it. Now coming to the decarbonization. Decarbonization is really challenging because these are all high energy intensive sectors, and you require a lot of conventional energy to it. While Gavin just now mentioned about renewable energy, while renewable energy is one lever which we have identified, but renewable energy is not available round the clock. Unless the energy storage technology matures enough, we will not have renewable energy round the clock. Renewable energy can only be 10% of one of the lever which can reduce 10% of the CO2 pool. But there are much more things which require to be done. I am very happy that my own company, ArcelorMittal Nippon Steel, is taking a step forward in this direction. We already have put up a roadmap till 2030 first. First milestone will be to reduce 20% of the CO2 emission, and then later on gradually move to net zero by say 50 or 60. Our parent companies have already committed for net zero by 2050. Some of the levers which we have identified is renewable energy is of course one. Alternative fuel will be another lever which we are working about. We would go for biochar, biomass-based fuels initially, and later on 2030 and beyond, when the green hydrogen is available in an economically viable manner, we would use green hydrogen.
I'll come back to green hydrogen in a bit later. Gavin, can I ask you about other difficult to decarbonize sectors? Industrial heating, for example. Is that something that can be decarbonized in the same way as electricity, or are there other challenges?
Yeah, so we actually just came out with a white paper, and if anyone wants to read it, you can find it. Look at my LinkedIn page. You can find a link there. So we just wrote a study about industrial heating. Industrial heating is it's about 20% of the total greenhouse gas emissions. And as Arvind said, actually iron and steel is a big part of that. Of the high temperature heating, which is about 55% of the total, almost half of that is actually for the metals industry. So a lot of the difficult to decarbonize sectors are in industrial heating. But about 30% of industrial heating is actually low temperature heat. So think like bakeries or food manufacturing,
ovens.
Pharmaceuticals. Yeah, ovens, cooking, things like that. Paint booths for drying paint on cars and appliances and things like that. Low temperature industrial heating is actually fairly easy to electrify. And it's one of those sectors where when you actually apply heat pump technology, because heat pumps take electrical energy in and then they boost the temperature of low-grade heat. So you can use waste heat and you can raise the temperature so you can reuse it. And actually that can get you free energy because the heat pump has a coefficient of performance. So you can get between a coefficient of performance of 3 to 4, meaning that you pay for the electricity, but you get 4 times as much energy in total heat from the waste heat that you recover. And in a lot of these industries also, the heat anyway is being rejected, so you're actually you're reducing cooling costs too. So there is an easy to abate part of even industrial heating. There absolutely is a very hard to abate part in places like the steel industry where you have to go to carbon capture or to hydrogen or to renewable fuels. But we need to look across the space and go for some of the options that are easier. The other thing also in industrial heating is there's a lot of opportunities to improve, particularly in the chemical industry, from better automation and better use of operational technology, so control systems by improving the set points and improving the way that energy is being used within the process industries.
Do you think that the rise of AI and things like cryptocurrencies, which all need huge amounts of energy and continually large amounts of resource and water and all sorts of things for their data centers and computing, do you think that these things are pushing back on the attempts by people like you, both of you, to reduce your own carbon emissions?
AI definitely helps.
Helps, you say? AI definitely helps?
Yes, it helps. How AI and machine learning, it's the process optimization. For example, we use a lot of coke in blast furnaces. Currently, it could be with the weighing scales and all, But with the help of machine learning, exactly how much of optimum coke is required to get that temperature, that is, AI is helping us out. So sometimes, we might be putting 10 to 20 kgs extra per ton of steel production. Now with the help of AI and machine learning, we exactly know that this much of heat can be generated by injecting 320 kgs of coal. So AI and machine learning is really helping us in optimizing the processes, and that way the energy required for melting of the iron ore.
Yeah, Gavin, I'd like to come back on that, but I'm saying that AI does help, of course, and please tell us more examples of that, because I'm sure AI and machine learning will help to make processes smoother. But also on the flip side, itself, AI uses a lot of energy, so I'd like to address that.
Yeah, okay, so if anyone was here in some of the earlier sessions, you heard people talk about the long history of AI and machine learning. So obviously in the automation industry, we love machine learning. We've been doing it for well over 40 years now. And there's a lot of applications in the process industries where you can use machine learning to get to more efficient process operations and reduce energy use. So the application definitely helps. The actual energy consumption of cloud computing or AI all actually happens in data centers. And from an energy efficiency standpoint, if you just look at this to begin with, you say, well, data centers, they're going to consume more energy. That's got to be a bad thing. But actually, the way that data centers consume energy is far, far, far more efficient than the computers, the PCs that we've had on our desktops. Right? Every laptop's got an inverter that's chucking out heat. Every PC's got a heater that's chucking out heat. All of that heat's going into offices. You can't reuse any of it. Once you consolidate all of that compute into a data center, you now have all the heat in one place. And that means you can actually collect it and reuse that waste heat. So here in Europe, there are really great examples. There already are several data centers running where the waste heat is rejected to district heating. So all across Scandinavia, it's now more or less mandatory. If you put up a new data center, you have to recover the heat and then use it for social heating. So the heat from the data center actually is heating the buildings. And typically it's used for low-cost social housing buildings that are nearby. So people are getting free residential energy that's coming from the data center. It's not quite free because they don't want it wasted, but it's very, very highly subsidized because they're reusing the data center waste heat. Now, you can't do that if your data center's a long way away from population, or if you're in a part of the world where you don't need to have heating. But you can still reuse the heat. You can, again, by using heat pump technology, you can boost the temperature and actually use it to drive direct air capture. So capturing CO2 out of air. When you look at capturing CO2 from the air, most of the operating cost is the energy required to regenerate the adsorbents. Some of it's for moving the air. So it's about 20% moving the air, about 80% is for regenerating the adsorbents. That 80% of the thermal energy can all be recovered from data centers. So you can actually pull more CO2 out of the, if you run the data center on renewable power and you pull CO2 out of the air, believe it or not, it actually becomes carbon negative.
This is very attractive as an idea. And Arvind, that was going to, it preempts a question for you. For your sectors, carbon sequestration, direct air capture, are these technologies you're thinking about? Can you use them?
Yes. Steel and cement, the conventional levers, what we discuss about, we can go about 50 to 65%. And the roadmap or the net zero roadmap, what we have prepared, at least 35 to 50% has to be captured, utilized, or sequestered. Without that, steel industry cannot be decarbonized completely. So definitely carbon capture and utilization is something which is very, very important for a steel industry. While there are solutions available at this point of time, but the market is not available. And also the economic viability of that solution also not there. So we first need to find a market for the products which are being converted from the carbon dioxide. And also, once the market is there, definitely economically viable. Once we scale it up, we actually would start getting the economical viable solution for it. Another one, I myself believe that the carbon has come from the earth, it has to go back to earth. So sequestration in long term, I would say, is the best solution, which are may be mineralization, may it be getting captured into the basalt formation, may it be getting captured into various other formations, but that's the way
it has to at the end. So end of life carbon would happen below the earth, while you can continue to change the use by converting into some useful products like ethanol, methanol, urea, and that kind of thing. But eventually it has to go below the earth.
Yeah, from our perspective, we're a supplier of carbon capture technology. So we've been in the business of CO2 separation from other gases since the 1960s. And last year, of 45 million tons of CO2 that was sequestered, about 15 of that was captured using our technology. So we have these solvents, we supply the sorbents that are used in a lot of other companies to pull CO2 out. For our own operations, in our own manufacturing plants, we're actually looking to deploy carbon capture on 2 of them. The key difficulty is not actually capturing the CO2. It's access to pipelines and access from the pipelines to injection wells. So in the United States, we still only have 3 certified wells. Around the world, there are not that many wells that are certified for CO2 reinjection. So you've got to be near to a pipeline that connects to a reinjection well in order to make a CCS project viable. And that's not the case in a lot of geographies at the moment. But particularly things like blue hydrogen, so making hydrogen by steam reforming of methane, capturing the CO2 and reinjecting it, that's one area where the economics is actually good already, because the CO2 is a high concentration stream. If you can get any kind of a credit for injecting that CO2, then that becomes very viable. So we are seeing adoption of carbon capture technologies in parts of industry where it makes sense to do so and where the government is supportive.
Arvind, can I talk to you about green hydrogen? You mentioned it earlier. Gavin just mentioned blue hydrogen. Would you just give us a quick description of all the different types of hydrogen quickly, and then why green hydrogen is especially useful for your sector?
Sorry, come again?
So if you can just give us a quick description of what all the different types of hydrogen. There's blue hydrogen, green hydrogen, and so on.
So some of the levers. So conventional lever, as I said first, renewable energy is first thing. Energy, solar and wind is something which is there. Now on the top of that, we are also going for energy storage. So energy storage again in 2 forms. One is hydro. So we are in the daytime when the surplus solar energy is available, we are taking the water to the top of the dam reservoirs, and from there in the night it comes down. So we get the renewable energy. The another solution is battery storage, of course. Nowadays, you know, the battery storage prices have started coming down, and I am very confident by 2030 it will be at par with the per unit rate which is there from the grid. The another solution is fuel switch. So we are trying to replace the conventional fossil fuel, coal or natural gas, by using the biomass or the biochar. The third one is, of course, utilization of scrap, more and more utilization of scrap. But the unfortunate part is, you know, since the steel consumption per capita was very low 20 years back, today we don't have sufficient scrap available. The third one is, of course, the next one is, of course, the biogas which is there. So a lot of biogas is being generated by the farmers, and that is being injected into the gas network. And then we have green hydrogen. So these are 4-5 technologies right now, and of course carbon capture and utilization.
So in terms of what green hydrogen is compared to blue, that's what I was asking before. In terms of how you make that, what's the difference, to just explain to people, and why is it green hydrogen that's the one that's useful to you? Yeah, maybe you can explain.
Yeah, if you want. So, so I have my little UNDP button here that shows the 17 United Nations Sustainable Development Goals. And when I wore this at a hydrogen conference, someone came up to me and said, wow, I'd heard of green hydrogen, blue hydrogen, pink hydrogen, gold hydrogen, brown hydrogen, but could you explain to me which is orange hydrogen? They thought this was all the different flavors of hydrogen. The biggest two, when people talk about hydrogen, they talk about gray or black hydrogen as being hydrogen made by steam methane reforming with CO2 emissions to the air. Blue hydrogen is steam methane reforming with CO2 capture. Green hydrogen is water electrolysis. So it can use, if you use renewable power, you can take water and just split water. We work in that sector. We develop actually the catalytic coated membranes for that. And green hydrogen is very advantageous in parts of the world where you have surplus renewable power, but it's not possible to export. So, for example, Western Australia or the Namibian desert, right? There's no way you're going to build power lines from Namibia to the UK. You can maybe build them from Morocco to the UK. You can maybe build them from Western Australia to Southern Australia, or from Southern Australia to Queensland, but you're probably not going to build power lines all the way across the whole of Australia to move power out of Western Australia. So there you can take the surplus renewable power, make green hydrogen, and then you can use it for either heavily energy-intensive industries like steel making, or you can convert it by reacting it with CO2 captured out of the air. You can even actually make fuels. So this is e-fuels, the e-fuels sector, which we're seeing a couple of projects now around the world moving forward in these desert areas where they have very cheap access to land and renewable power.
Thank you. That's very clear. That's very interesting to hear. Arvind, quickly from you, how important is the government in regulating industry in general, but also the energy sector, to making sure that net zero is something that you can achieve together, because you can't do it by yourself?
So initially government's action was very slow, but I can see that now it's catching up with the speed, and lots of regulations are coming up in emerging economies. So you have the carbon markets coming up, you have green steel taxonomy coming up, you have government is procuring green steel and promoting green steel as well. Similarly for the green steel also, government is coming out with the national mission on the steel making and scrap, promoting the scrap utilization. So the steps, government is taking all the right step in the direction to decarbonize the industry. Government is also trying to incentivize while they are trying to put the penalty, but there is both carrot and stick mechanism is being used by the governments.
Can I ask you both in the last few minutes? Maybe, Gavin, you can start. We've got 3 minutes left. If you can take a minute each just to say, what do you think is the biggest unsolved challenge in this sector that we're talking about of net zero, whether it's industry, the energy sector, government regulation, but the willpower of people? What is it that's the biggest unsolved challenge to getting to this target that we've all got?
It's a good question, Alok. I'd say I'd split it into two things, right? The first one is the sort of adoption challenge, right? That you've heard the saying, the future's here, it's just not evenly distributed. So there are a lot of parts of the space where we know the technical answer. We have good technical solutions. Now, they might currently be slightly more expensive than conventional alternatives, but with some push they could get there. There are many really, really good technologies that actually save money, but are not widely adopted. So for example, demand control ventilation in buildings, right? It saves energy, it's very cheap to implement, and yet even in developed economies, less than 1 or 2% of buildings actually have demand control ventilation.
What is demand control ventilation?
This is where you monitor the PM 2.5 or the CO2 in a building, and you actually control the amount of air that comes in from outside. So if you think about a building, if the building has extractor fans, then it sucks air from inside, and it's actually at below ambient pressure, and there's no control over how the air's brought in. If you have a building where you actually blow the air into the building, you raise the pressure, and now you've actually can control the ventilation rate. And that means that if you're in a heating area, like in Europe or North America, you reduce the amount of air that needs to be heated. If you're in an air conditioning area, you reduce the moisture load on the building, and you reduce the air conditioning duty. So you get about 30% energy saving just for the cost of a slightly more sophisticated controller. So great technology, not very widely adopted. Most people don't know about it. People don't ask about it. So there it's really just a question of driving more adoption. And key to driving more adoption is actually making sure that every country around the world is resourced to adopt these technologies, right? So making sure that we are actually contributing, that the rich countries are actually contributing to the adoption of green technology in the global south is critical to getting to net zero faster. But even when you do all of that and you apply all of the things that are currently known, there's still a need for some technical sectors where we don't yet have good solutions. Heavy-duty freight is a good example. So there are still hard-to-solve technical problems that need research, but adoption is the key thing to get to net zero faster.
Thank you, Gavin. And Arvind, last word to you. What do you
So one unsolved challenge which we have is the challenge of finance. While technology is there, policies will be there, but who is going to solve the challenge of finance? Because we develop lots of roadmap, and when we try to implement the roadmap, on an average the cost of decarbonizing 1 ton of steel or 1 ton of cement is close to around $230. Now when you are selling cement at $80 a ton, and when you are selling steel at $450 a ton,
who is going to pay for that additional $230? Consumers are definitely not willing to pay. The developing economies are not going to pay. So unless and until this challenges has been sorted out, I don't think decarbonization on net zero will be possible.
All right, guys, thank you very much for both of you. That was fascinating. There's people in the audience who've probably got questions, so if you've got questions, please do come up to them afterwards. But in the meanwhile, can I have a round of applause for our panelists?
Thank you.
Thank you.
Thank you.
Thank you.